So now in this chapter we analyze a very simple thing which is single queue, and in the next few chapters we'll move on to the networks of queues. So we start with birth processes again, as we saw, and then apply them to analyze MM1 queue, MMM queues, and the book has MMB queues and other queuing systems. We won't be covering that in the class. We would be just doing MM1 queue here in the class, and then the same methodology you can apply to other queues which is in the book. So I would expect that you will read that before the exam. So birth process. So we remember birth processes where you had for each state you could have a birth rate and the death rate, arrival and departure. And so basically then, so there are states which are, and you just go to the adjacent state. If you further simplify this thing, where the arrival rates are all same and the departure rates are all same, then you get, actually before we simplify, let's just analyze this complex thing itself. You can get the answer for the complex thing. It's not very difficult. Sorry, I'm going in the right direction. Okay, right here. So we can analyze it. We can just look at the state J and see how long we will stay here, because we are going to get out at the rate lambda J to the next one, or get out at the rate mu J to the previous one. So you can write down an equation like this. You can say my probability at time t plus delta t being J plus 1 going to the next state, if I am in J state, is the arrival rate times delta t. The probability of my going to the previous state, which means to being J minus 1 when I am at J state J, is mu J delta t. Right? This is the departure rate. So in time delta t, this is the probability of departure and this is the probability of arrival. And so my probability of my staying at the same state where I am is 1 minus those two probabilities. There are only 3 possibilities in time delta t. Delta t is very small. So if you write this for all the j's, then you get something like this, where P0, the probability of being in state 0, and state 0 does not have any previous thing, so there is no mu here. And then you write down that. For P1 you write down, for P2, and so on and so forth. And then you can bring the terms, proper terms on this side. So P0 t plus delta t, and you bring P0 delta t on this side and divide by delta t. Then you get an expression which says dp upon dt is this value. And under steady state dp is 0, and therefore this whole thing is 0. So you can write down that expression. And when you solve those equations, you will get equations like this. You will get that Pj plus 1 is mu j plus lambda j upon mu j plus 1 times Pj minus blah blah blah. So this is the equation you will get. And in particular for P1 you will get lambda 0 upon mu 1 P0. And if starting with this, you can calculate P2, P3, P4, P5. And you will find out that the Pn is very simple, this formula, which can be written in a more complex form as a product of lambda j upon mu j plus 1. Alright, so this is something that if you wanted to derive it, and actually you will not have to derive in your lifetime, because somebody has already derived it and published it, so there is nothing much to do here. But you have to know how they derived it, right? And so that is there, right? What we are going to do more importantly is to use this, now that we have derived it, to use this for all the queues that we are interested in. Oh, by the way, once you have gotten all the probabilities, then they have to add up to 1, and if you add up all of them to 1, then you can calculate P0. So P0 will come out to be 1 upon 1 plus this expression. So let's apply this to MM1Q. Now MM1Q is very simple. In MM1Q, only the arrival rate is always lambda. So regardless of how many people are in the queue, the rate doesn't change. Right? It's memory. It's basically memoryless, and so lambdas are all equal. Similarly, the service is all mu's are all equal. So this is much simpler case than the previous we just derived. Right? Regardless of what state the system is, the service rate and the arrival rates don't change. So if you removed all those in the previous formula, basically all lambda n's are equal to lambda, all mu n's are equal to mu, then your first formula becomes Pn is equal to lambda upon mu raised to n P0. If you call this rho, then it becomes Pn is equal to rho raised to n P0. What is rho? Rho is the arrival divided by the service. If you have two arrivals per second, and you have service which is let me change it around. Suppose you have one arrival per second and you service 2 per second. Right? Then lambda upon mu would be 1/2. So that is your basically the load. That is your utilization. That is what we call traffic intensity. Right? Rho is the traffic intensity or the utilization. I mean, actually, I'm not going to call it utilization because in a minute we will see it could be different. But so that is the traffic intensity, arrival divided by departure rate. So Pn is simply rho raised to n times P0. And you can calculate now P1, P2, P3 to P infinity. They all add up to 1. And so you can calculate P0. P0 would be 1 upon P0 plus P1 plus P2 and so on and so forth. All of these values, they add up to, and you can add up the infinite series, and that will come out to 1 minus rho. Right? Everybody knows how to add up this series? Right? Okay. So if you add up this series, you will get the whole thing as 1 minus rho, and then Pn is equal to therefore P0 times rho raised to n. And you can calculate for any n, you can calculate it and plot it. You will find out that the n is geometrically distributed. This is geometric distribution. Now, utilization. In this case, for MM1Q, the utilization is simply the probability of having one or more jobs. That means probability of having basically 1 minus P0, which happens to be P0 is 1 minus rho, 1 minus P0 is rho. So utilization is equal to rho for this particular Q. All right, and then we can calculate the expected value of n. How? Because we know the n and the probability of n. We just multiply n by probability of n and add up from 0 to infinity, but 0 doesn't really matter because when you multiply by 0, that cancels out. So 1 to infinity. And n is given here, probability of n is given here. This is an infinite series which you know how to add up. If you add up that series, you will get rho upon 1 minus rho. You can calculate the variance of the number of jobs in the system. How? You can calculate the expected value of n squared and subtract the expected whole square of the expected value of n. N squared expected value you can calculate by multiplying n squared by its probability of n. And then we already know En. So we subtract that. And this is an infinite series which again, if you know how to add the infinite series, you will add up all that and come out rho upon 1 minus rho whole squared. And so on. So actually you can calculate not only the mean variance, you can calculate the third moment, fourth moment, infinite moment, and you can calculate the probability density function, and you can calculate the probability distribution function. Everything about n can be calculated. Yeah. What is the moment? So actually the expected value of n square is second moment, expected value of n is the first moment, expected value of n cube is the third moment. Expected value of n raised to k is kth moment.
But what does it mean?
But
what does it mean?
Oh, basically, okay, let me. Moments are useful for certain things. When you go into advanced statistics, which we are not going here, one way to find a density function is to just get all the moments and then you can combine them into a density function. Okay, using Laplace transforms. We are not at that level, so we won't go in there. But basically, all I wanted to say was that we already calculated two things. We calculated the first moment and the second moment here. You could do other moments as well, and then you could get all these results. Okay, so these results are in the book actually. This is box 31.1, and given lambda and mu for the MM1Q, you can calculate. First of all, it has to be, for the Q to be stable, the arrival rate has to be less than the service rate. So rho has to be less than 1. If rho is equal to 1 or more than 1, the Q is not going to be stable. It is going to continuously increase. So probability of 0 jobs in the system is 1 minus rho. Probability of n jobs in the system is so much. Mean number of jobs variance, we already derived this much. Then there is probability of k jobs is this value, if k number of jobs in the queue. Okay, actually this should be called number of jobs waiting. And then number of jobs, mean number of jobs waiting. So now this is the average value of that thing. And so this one doesn't include the jobs in the service. Okay, then the variance of that, and then the cumulative distribution of the response time is also people have derived, and this comes out that mean response time, if you know the distribution, you can calculate the mean, and that is that value, variance, and so on and so forth. More. You can calculate the qth percentile, you can calculate the 90th percentile, you can calculate the mean waiting time, and then all the percentiles of the waiting time. You can calculate the probability of jobs in one busy period. What is a busy period? So basically the system starts idle, no people in the queue. Then queue builds up, and then the queue dies down, right? When the queue dies down, then the busy period is over. Time to take a coffee break then, right? Then the server takes a coffee break, and then suddenly the first job arrives. When the first job arrives, the next busy period begins, right? So that length of the period over which the job is, there is always one or more persons in the queue, that is called a busy period. Okay, so probability of n jobs in that one per busy period, people have derived that, and mean number of jobs served in one busy period, and so on and so forth, and so on. So there are lots of formulas. I don't expect you to remember any of those, except you do have to remember rho is equal to lambda upon mu, because that is just ingrained, in the brain. Rho is equal to lambda upon mu. But then, if I have to look up the number of n jobs, then I have to go to that box. Okay, now you can do lots of useful stuff. So here's an example. On a network gateway, measurements show that the packets arrive at the mean rate of 125 packets per second, and the gateway takes about 2 milliseconds to forward them. Now this is an average number, even though it says about, actually all we are saying is it takes a mean of 2 milliseconds to forward them. Using MM1 model, analyze the gateway. In particular, tell me what is the probability of buffer overflow if the gateway has only 12 buffers. How many buffers do we need to keep the packet loss below 1 per million? Right, so let's do it one at a time. What is the arrival rate here? 125. What is the service rate? Now remember, these are the rates. So if you are given a time, you have to somehow do opposite of that, invert that. So here it says time. It takes 2 milliseconds. So we divide 1 by 2 milliseconds to get 500 packets per second as the service rate. Once we know lambda and mu, we can calculate the rho. Rho is lambda upon mu, and that is 0.25, 1 quarter. Once we know that, then probability of n packets in the queue is so much, 0.75 times 0.25 rho. Mean number is rho upon 1 minus rho, rho times rho upon 1 minus rho, so that is 0.33. Mean time is spent, again another formula, 1 upon mu divided by 1 minus rho is so many milliseconds. Now here is the interesting thing, probability of buffer overflow. What is the probability of more than 13 packets in the gateway? Okay, if you go back to the book, here it says probability of finding n or more jobs is very simple, rho raised to n, right? N or more. So this is the probability of n plus 1, n plus 2. You add up that whole series, that adds up to rho raised to n. So we use that. So probability of more than 13 packets, so 14 and up, okay, is this value. So we have, that is 4 packets per billion packets. So that turns out to be 4 packets per billion packets will get lost. When if you have 13 buffers, 14th packet when it comes, it will be dropped. So this gives you the probability of that happening. Now, to limit the probability loss to, if you just want 10 raised to minus 6, then you calculate rho raised to n, and then you get 9.96. We need about 9 buffers. So the last two, now here's the problem though. The last two results about the buffer overflow are approximate. Why they are approximate? Because if you really wanted to model a queue with 13 buffers, that would be not MM1 queue. That would be an MM1/13 queue. Right? Remember, the fourth parameter in the queue notation is the number of buffers. It's a different queue. It is discussed in the book after 2 sections, but first is the MM1 queue, and whatever results we got, we should really get it from MM1 queue. With MM1 queue, you can get the little bit more accurate number. Other number will not be very different given this row. And second thing is, there are so many other assumptions here that it doesn't really matter, because Poisson assumption and constant arrival, so on and so forth. So given engineering considerations, I think this is good enough result. All right. So here is a quiz, just to check that you guys can do it. I could, we could do the quiz or we could give it a homework, but let's do it as a quiz now that it is here. So average response time on a database system is 3 seconds. So that is the response time. During a 1 minute observation interval, the idle time on the system was measured to be 10 seconds. So this is the idle time, 10 seconds in 1 minute observation. So from there you can figure out how busy the system is. Right? Using MM1 queue, determine the following. So first of all, given these 3 things, 3 seconds is the response time, and we know the formula for the response time is ER is equal to 1 upon lambda, 1 upon mu time divided by 1 minus rho. So that is how you can figure that out. During a 1 minute observation, you observed for 60 seconds and it was measured to be 10 seconds. The idle time was 10 seconds. So you can figure out what the busy time was, and therefore, during 1 second, and you can figure out what the rho was. So you know ER and you know rho now. So then you can figure out mu and lambda. Once you know mu and lambda, then you can answer the next one. What is the arrival rate? What is the service rate? And then average number in the system. So that number. Please do it. So we are given ER. ER is 3. So 1 upon mu divided by 1 minus rho is 3. And rho is given to be 50 upon 60. Why? 50 seconds is out of 60. I don't know how many people got to that line. If you got this line, then everything else is simple. Once you know rho, you can calculate mu from here. Mu comes out to 5/6. Once you know mu and rho, you can calculate lambda. That comes out 5/3. And once you know lambda and mu and rho and everything, you can calculate En, which is what we needed, rho upon 1 minus rho, 5 jobs. Any question about this? Can you do it now? All right, if you can do it, then move on. MMMQ. Now, MMMQ, basically, the way it is different from MM1Q is that after m jobs in the system, the behavior changes. Before m jobs in the system, the service rate cannot be more than the number of people in the system. So when the first job comes in, one server becomes busy, service rate is mu. When the second job comes in, the two servers become busy, the service rate is 2 mu. When finally like this, when m jobs come in, then the service rate here is m mu. So this is slightly different than MM1, right? If you now you can use the same formula that we derived for birth death processes, and you can get everything else that we have talked about. You can get P0, you can get Pn, and so on and so forth. Many of these formulas use this expression, and it's called var rho. So this is var rho is equal to that one. And that expression is used in many of the formulas. Then, now here thing, this is, I am going to just do it so much here in the class. The derivation of all this and the examples of all this is in the book. Please read those examples, and should be straightforward application. Then the next queue is MMMBQ. Now this is slightly different than the previous queue in the sense that after B jobs arrive, the system doesn't go any further. Right? With the B jobs in the system stops right there, and the service rate is m mu. Hopefully B is more than m, and then basically, and hopefully what I mean, like basically you will have, if you have 3 servers and you have 2 buffers, that would really be bad. So basically this is the system, and then you can write down the expressions as before. When you add up all the probabilities, you don't go up to infinity, you just go up to B, and you get these expressions. Yeah.
When you say that the system doesn't go any further, the jobs are what?
Yeah, exactly. So there is a loss rate, and the loss rate is equal to lambda times P sub B.
Should that also be n plus 1 times mu?
Yeah, all these numbers are going to be
You only have M
corrected.
servers, so
Huh?
you only have M servers, so you can't possibly go past MU.
Oh, yeah. That was the mistake, the last one. I made a mistake in a hurry. That's a good one. Thank you. So, yeah, this correction was wrong. That's why I don't do corrections live. There's not enough time to think. Now, on the next one, this is m mu, m minus 1 mu, so everything else is m mu. Good. So that is correct. This is all correct. M mu is here, and everything else is m mu after that. Anyway, so these formulas are all there, are actually more formulas in the book. The interesting thing to read is that the utilization is not rho. See, in the MM1 queue, the utilization is rho. In MMB queue, the utilization is rho times 1 minus PB. So that's why we don't call rho as utilization. Rho is called traffic intensity. All right? And then the book also has other queues, MG1, MD1, MG1 with processor sharing, MG infinity, GM1, GG1. Now, you don't have to basically remember any of these. I don't remember any of these, but you have to know the existence of these queues. So whenever they happen, we go to the book, we read the box, and we use the formula. And that's all we need to do. All right? In particular, GG1, GGM is interesting because GGM means any arrival, any departure distribution, service distribution with M servers. So all these results are there, okay? That brings us to the end of this chapter, and the 5 key points are that the birth-death processes basically allow us to compute the probability of n jobs in the system. So that is why we covered birth-death process in the first place, is because that helps us get all these queues, MM1, MMM, MMB queues resolved. Now with MM1 queue, totally load independent, all the arrivals and service times are same, and therefore you can solve it very easily and the traffic intensity is rho upon mu, and you can get all those formulas, right? With and with other Q's, basically you have the formulas again as before. Homework 31. So this homework basically asks you to just use for MM1Q all these formulas, which include getting which includes getting 90 percentile and other things. Just you have to use